So the last remaining topic here in radioactivity is about nuclear fission. Nuclear fission is a process where, due to the great instability of certain types of isotopes, we can artificially create isotopes that are so unstable that they end up ripping apart at the seams. And as a result, we don't just get an alpha decay or a beta decay or even a gamma decay. We get two completely new nuclei and a whole bunch of energy and a whole bunch of free neutrons. And, oh yeah, by the way, a whole lot of radiation. So we still get gamma, but we get way, 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 way more of it. So this process is known as nuclear fission. Fission is the splitting of atoms into multiple pieces through this artificial creation of these unstable nuclei. And when that atom splits, we get two new nuclei and we get a whole bunch of energy and one or more neutrons. And this part is especially important because it is usually neutron bombardment that causes nuclear fission in the first place. So we hit a big atom with an extra neutron. That extra neutron causes the isotope to become very, very unstable. It breaks apart. We get two smaller nuclei, and we get more neutrons that are ejected at these high speeds and high energies that can go out and disrupt other nuclei and make potentially other fission reactions take place. So pictorially speaking, this is probably the most common reaction. Uranium-235 gets bombarded with a neutron to make uranium-236. Uranium-236 is incredibly unstable, and it breaks apart into barium-140, krypton-93, gamma rays, energy, and three other neutrons. And those three other neutrons flying out here on the back end can go and bombard themselves into other uranium-235 atoms and start the whole process over again. Now, nuclear fission does not occur naturally. Its close cousin, nuclear fusion, which we've been trying to do here on planet Earth for about 40 years, maybe even longer, to pretty much zero success, occurs in stars. In nuclear fusion, we take small light nuclei like hydrogen and under intense temperature and pressure, bring them together to form an atom of helium. And in the bringing together of that atom, it actually releases a ton of energy. It is that energy that ultimately makes a star hot. All that extra energy gets burned, comes out, and we see heat and light coming from stars in outer space because of that fusion reaction. From an energy standpoint, it is much more efficient than nuclear fission is, but fusion is almost impossible to do here on planet Earth. We can get the pressure, but we usually can't get the temperature high enough. Because most things that can get up to the temperature of, say, the sun, aren't made out of materials that can withstand temperatures of the sun. And so that's been the problem overall. But nuclear power is done using fission reactions. And fission reactions largely are just where we take a nuclear fission in some kind of closed container, we get that fission to occur, and the energy from that fission ultimately creates a ton of heat that is then used to warm up water and turn it into steam, and the steam turns a turbine, which turns a generator and produces electricity. The process is very effective, but it also is somewhat inefficient. As we talked about in the previous chapter, water requires a ton of energy in order to turn it into steam. So a lot of the energy that is created by the nuclear reaction goes toward creating the steam and not actually converting it into any kind of electrical power. So there's a good bit of heat loss along the way. But pound for pound and gram for gram, we get far more energy out of a nuclear power plant in terms of nuclear fuel than we do out of the more conventional ways of creating electricity. Does anyone know the primary means of energy production here in Indiana? It's coal. We've got tons of it. It burns really easy. And basically we use the coal burning in the same kind of way that the nuclear power is. We burn coal, coal heats up water, water turns to steam, steam turns to turbine, turbine creates electricity. Same process, different starting material. Now, why do we use coal? Again, plentiful, cheap, and well, it used to be a lot dirtier than it is now. We still have a lot to deal with in terms of carbon dioxide production, but the coal gasification process has reduced a lot of the side products that come off of coal-fired power plants considerably. Chemical scrubbers in the stacks have reduced some of the sulfur and nitrogen emissions that come from coal burning as well. They do, but they don't catch everything. You gotta figure carbon is coal, or coal is carbon. So every single gram of carbon, or at least most of it, is going to turn into more grams of carbon dioxide once we add the oxygen to it. And the CO2 scrubbers do a good job, but they can't prevent all of the carbon dioxide from going up. And so from an environmentalist standpoint, coal-fired power plants are pretty heavy greenhouse producers. And that's one of the reasons why you see, as we go from administration to administration, from a presidential and EPA standpoint, the party of the EPA comes in, wants to put in a whole bunch of restrictions, carbon caps, and whatnot, to try to get us to stop using coal and start looking at other renewables. And the other party says, well, no. This is cheap. It's easy. It's better for the economy. Let's just find better ways to do it. So we go back and forth, back and forth. 10 years ago, it was one way. 5 years ago, it was a different way. Now, well, we'll see what happens under the current administration, but probably have a pretty good idea. So this is how a nuclear power plant works. This is a mock-up. In here, you've got the control room. This is where Homer sits. And make sure that everything is working in tip-top shape. The actual the water tanks are and the pump house are here. Water does have to be pumped in continuously from an outside source because there's no efficient way to cool all of the water in enough of a sense that we have to be able to cool it down enough so that the steam can kind of come back down so that we can put it back into the reaction vessel without it bursting the pipes with the excess pressure. So water is in and out. The stack here is for excess steam. So when you think about those big towers that we associate with nuclear power plants, those are actually cooling towers. The purpose of those towers is to let off excess steam. And so most of what you see coming out of those towers is not radioactive material at all. It's water vapor. Because those are steam stacks. They let out the excess steam so that the pressure inside of the lines doesn't get too high. Inside of here, this is the reaction vessel itself. And so the nuclear power is generated in here, is then used to take the water. The water gets pushed through the lines here to turn the turbines. The turbines are connected to the generators. The generators eventually are deposited into these transformers. And the transformers are used to carry the electricity from the power plant to other locations. Once the nuclear fuel is spent, the used fuel rods are held in one storage pond. The residual waste, the barium and krypton wastes that are generated are put into a different pod. And right now, the best we've got in terms of storage is just simply storing it underground in a concrete kind of facility. And I hate saying it, but kind of just hoping for the best. Gamma, yes, gamma is produced initially. Now, most of that gamma energy, most of that gamma is contained inside of the vessel. And most of that energy is ultimately dissipated in the conversion of the water to the steam. Remember, gamma is pure energy. It's ionizing energy, but it's pure energy. So the majority of that, the ionizing radiation part of it is contained inside of the reaction room. Most of the energy itself goes into the water. Where we run into problems is when the reaction vessel, the nuclear reactor, gets breached somehow. And there have been a few occasions where that has happened. Now, what are our issues? The wastes themselves are usually radioactive. So one of the waste products that we showed you in the previous slide was barium-140. If you look at the periodic table, most common forms of barium are 137 and 138. So that barium is still active and will likely undergo several decays of its own to get to a more stable form. The krypton-93 is probably the more dangerous of the two. Krypton's atomic mass is about 84. The krypton that is generated by this reaction has a mass number of 93. So it's going to go through several, possibly 8 or 9 transmutations to get to something stable. All of those transmutations take time. All of them generate radioactive particles as they do. So how we deal with those wastes, how we store those wastes, is of a particular concern. like I said, right now, the best solution we have is just storing them in concrete, which we know blocks the radiation. But the issue that we've got to run into is, what if that concrete barrier is breached? Now you're underground, and who knows, maybe you hit the water table and now you've got radioactive materials in your water. There's a lot to consider there. The other thing is that the materials themselves corrode most common goods. So you've got to be able to find materials that will not corrode under the stress of holding those radioactive wastes. Now, we talked about the idea that when a fission reaction occurs, we get these neutrons that are generated. Now, in a nuclear power plant, there are checks and balances to the nuclear power itself. Inside of the nuclear power plant, inside of the reactor, there are neutron rods. The whole point of those neutron rods is to absorb those excess neutrons and keep the control of the reaction so that it doesn't spin too far out of control. The other thing is that we rarely have what is called a critical mass. Critical mass is the minimum amount of fissile material necessary to start a chain reaction. When you think about chain reaction, you need to think more about Hiroshima than about Springfield. Critical masses are necessary for making nuclear weapons. So one of the reasons why atomic bombs work the way that they do and cause that massive destruction is we get some sort of generation of the fission reaction to start, and then the chain reaction occurs. We get all of this energy, all of this pressure, all at once. The bomb explodes. The energy dissipates in lots and lots and lots and lots of directions. And with it, that big burst of radiation, gamma radiation, which is why, again, when you think Hiroshima, you think massive destruction, massive death, and really none of the people there could have done anything to stop it, unless they were able to get several feet underground, but they weren't even sure it was coming to them. Now, in a nuclear power plant, systems malfunctions can lead to criticality. The fuel rods are supposed to be put in on a staggered cycle. If all of them were put in all at the same time, that could potentially lead to a critical mass. Now, again, control rods, neutron rods are supposed to be in there to curtail the reaction, slow it down. But again, if there's a systems malfunction, we can kind of see the opposite happen. And such is the case in these three nuclear disasters. First one we'll talk about, 3 Mile Island in Pennsylvania. This occurred in 1979, so this was not that recent, but also not that long ago. Basically, what happened is that they didn't have a criticality, they didn't have a reactor meltdown, but what they did have is that they had a leak, and some of the coolant from that reactor ended up getting into the atmosphere, and as a result, ejected some radiation into the surrounding area. It was not a big thing. No one died. Very few people got sick directly, but there was an increase in cancer rates in that area over the period of the next several years. But that was the only thing that really happened. It had an impact on us as Americans, though. Very few power plants have been built since 1979 because of 3 Mile Island. 3 Mile Island is often pointed to as one of the reasons why we shouldn't build new nuclear power plants. The only ones that are getting built now are for military use. The other one that gets pointed to often is Chernobyl. Chernobyl is a city in Ukraine, which was formerly in the USSR, now is part of, well, Ukraine. 1986, number of things happened. First of all, communism's declining in the USSR, and so the power plant itself is not properly equipped. Instead of having a staff of people to monitor all of the different things, they had a skeleton crew of, I want to say like 5 people running a nuclear power plant. Some things went wrong, as you might imagine. We ended up getting a power surge. Power surge causes a critical reaction to occur in one of the reactors. One of the reactors downright explodes. Leaves a massive crater inside of the Ukraine and a nuclear cloud that travels all over Western and Eastern Europe. So the radioactive fuel and byproducts get shot up into the air as part of the explosion. Russia, Ukraine, Belarus, several other countries in Eastern Europe get a significant dose of radiation. Due to the explosion itself and the radiation that was directly released by the explosion, 56 people die. It is also estimated that about 5 million people have their health impacted in some kind of way, whether it's an elevated risk of cancer or some form of radiation sickness. 5 million people are sicker as a result of this than they were the day before. And going back to about 2005, that was the last number I could really find. Incidences of thyroid cancer are significantly higher in the region compared to other regions. And so again, do the math on that one. That's almost 20 years of radiation. And still, there's enough radiation in the area that we see it affecting the health of other people that live there still. Most recently, Fukushima, Japan, 2011. Some of you might remember this, depends on how old you were when this happened. But basically, there's a massive earthquake in the middle of the Pacific Ocean. That massive earthquake, an 8.9 on the Richter scale, causes a several 100-foot tsunami to come crashing over Japan, including this nuclear power plant on one of the islands. The resulting tsunami causes the cooling systems to fail inside of the power plant, and there is a partial meltdown of at least 3 of their nuclear reactors. Now, none of them explode, mind you, but we do see a partial meltdown, and as a result of that partial meltdown, some radiation is released. Some people do get injured because of the radiation. Nobody dies, but some people do get sicker as a result. Now, the main reason, you might be asking yourself, well, why would you put a nuclear power plant right on the shoreline? Well, you got to remember, Japan's a pretty tiny island. So there's not a whole lot of inland that isn't like on the top of a mountain. And the other reason is, remember that you need water to run a nuclear power plant, because you got to get a fresh supply of water to replace all of the stuff that's coming out as steam. So in island nations, they put their power plants right on the shore so that they can bring in fresh seawater to act as a coolant and to provide themselves with water. Tsunami hits, water pumps get knocked out. Instead of getting cooler in there, it gets hotter and hotter and hotter in there. And they don't recognize the problem because of, well, you know, the tsunami, to shut off the nuclear reactors until it's too late. Again, nobody's killed. We get a few people that are treated for injuries and radiation. Most affected group are the infants and the young children in Fukushima, whose overall probability for getting cancer goes up by 1%, which is not an insignificant total. All right, these are the 3 disasters. So this is 3 Mile Island here on the top left. You can see why it's called 3 Mile Island. It is literally just a little island in the middle of a river in Pennsylvania. This crater here is what used to be Chernobyl. And then this was the Japanese Navy fighting the fires that had erupted as a result of the energy outbreak as a result of Fukushima. And so that's it for our unit here on radiation and on radioactive materials. On Monday, we'll start looking at corrosive materials out of chapter 8, which, while not as, you know, cool as this, there are a lot of corrosive materials make up a big chunk of the kinds of hazards we encounter on a daily basis. So I'll leave you with that. Have a great weekend.